this may or may not work. So I'm letting you know in advance. Okay, so what I want to do is look at the behaviour of this series. Now I've got the series in the work file here, so if I just take a look at this, what I've got is monthly oil consumption for the US. It's measured in thousands of barrels a day, and I've just put a link there to the data source, so you could actually go and check it out if you wanted to. Okay, now as I said, the first thing we need to do whenever we're looking at a data series, we're trying to fit a model to a data series, is we need to actually look at what that series looks like. So if I click on the series here, this opens it up in spreadsheet form, and then if I go to view here, I can go to graph and plot a graph of the series. Okay, and this is my time series, and we saw it on the slide a minute ago. It's dominated by that strong trend. Okay, that's the main feature we'd notice about it. Okay, now if we're trying to fit a ARIMA model to this, then the basic tool of analysis we have is the correlogram. You know, the correlogram is the basic thing we look at to try and fit a model to data. I pretty much know by looking at the graph of the series what the correlogram will look like, because I know that this series is not stationary, and I strongly suspect that the first thing I'll see from the correlogram is a set of autocorrelations that die down very slowly to zero. Okay, but just to confirm that's the case, let's take a look. So if we go to view here and then go to correlogram and look at a correlogram of the level of the data there, okay, you can see that it's pretty much as I said. When we look at the set of autocorrelations of a series like this, then we see autocorrelations that start off close to 1, 0.921, and then die down very slowly to 0. And this is characteristic of a series that is not stationary or contains a unit root. Okay? So the first thing I'm going to do before I do anything else is I'm going to difference the series in order to remove the trend, or to allow for the trend. So let's see how we do that. Well, if I go here to the command line and I type in the command, okay, show, I'm going to take the first difference of the log of this series, because I'm going to work with a log series here to allow for the fact that it's growing through time. So I'm going to type in dlog oil C. Okay, and that brings up the first difference, the logarithm of the series. Now what this is giving me effectively is the month-on-month growth rate of the series. Okay, it's giving me the proportional change in the series with respect to every month. So what I'm going to do now is look at that in a different ways. If I look at the graph of the series first of all, okay, you can see that by difference in the series I take out the trend. Okay, if I take the first difference of the series, it removes the trend, so we get a series that now doesn't have any strong trend in it. Instead it just seems to be sort of fairly random variations around a constant mean, which is what we want. We want to take out that trend. Okay, now we want to see if there's any systematic information in this series which can help us explain its behaviour. So we need to look at the correlogram of the difference series here and see whether or not there is anything to be explained here. Is there any information here that we can exploit? Okay, so if I go to view here and then go to correlogram, click on correlogram here. Okay, now if I look at this series here, okay, the correlogram, you see the correlogram now looks very, very different from the first correlogram that we looked at. By difference in the series, we've got rid of that feature where the autocorrelations die down slowly to 0. Instead, what we seem to be picking up is a very significant first order autocorrelation. Okay, we've got the first order autocorrelation is quite large. It's outside these bands here, the standard error bands given by the broken lines here. So we seem to have a significant first order autocorrelation. But then after that, they seem to die down fairly quickly. They seem to disappear. So the second order autocorrelation is actually quite small. And the third and fourth ones are also very small. Now this is characteristic of a moving average process. If you remember in the previous lecture we talked about moving average processes, and when we look at the parallelogram of the moving average process we get a single spike in the autocorrelations. Okay? And that's what we're observing here. A single spike in the first order autocorrelation, after that dies down fairly quickly. So what I'm going to do to start off with is to fit a first order moving average process to this series in order to see whether or not that will capture at least part of the behaviour of the series. Can I just pause there and ask if anybody's got any questions? No? Okay, well let's see what we get. Yeah.
Why you just at the first time you use log?
Why do I use logarithm?
Yeah.
The reason I use...
Just use the first order of the...
I could just use the first difference, to be perfectly honest. Oh, so the question was, why have I taken logarithms here? The answer is, if I have a log series, and there is a trend in the log series, then that's equivalent to the series growing at a constant rate through time, a constant proportional rate, certain percentage per annum or whatever. Okay? To be perfectly honest, I doubt that it will make very much difference here. Okay? I think if we take the level of the series or the log of the series, it's not going to make a huge difference. But the reason I've taken logs is because it allows for that constant proportional growth rate. Okay? Anything else? Okay. I should say, by the way, this kind of work, ARIMA modelling, to be frank, is really more of an art than a science. Okay, a lot of it is fitting the best model we can by looking at things like the parallelogram and trying to get an intuitive feel for how the series behaves. Two different people coming at the same data set can come up with different ARIMA models. Okay, but they will probably capture the same things in slightly different ways. So there's not always a perfect ARIMA model that everyone will agree on, but most people will probably come up with something fairly similar. Okay? Right. Anyway, let's take a look at this one then. What I'm going to do is I'm going to fit a moving average process to this. So I'm just going to shut this window down, and I'm now going to estimate my first model. So to do that, I'm going to type ls for least squares, and then dlog of oil, that's going to be my dependent variable, and I'm going to regress that on a constant, and I'm going to put in a first order moving average process, MA1. Okay, oh sorry, it's oil C for consumption here. There we go. Hit return. Okay, and this has estimated my model for me. Okay, so we've regressed the first difference, the log of oil, on a constant and the first order moving average term. We've got a coefficient of minus 0.76 on the moving average component, and the t-statistic is minus 20.1, so it's quite significant. So we see that we are actually capturing something really quite important here with this moving average term. Look at the r squared for the regression. The r squared is 0.367. So just by putting in this moving average term, we're explaining or capturing about 37% of the variation of this series. So that's quite a lot, given that, you remember looking at the series, there's a lot of variation there. So we're doing quite well just by our first attempt here. Okay? The other parameter it reports here is sigma squared. This is actually an estimate of the residual variance. Okay, so when it does these ARIMA models, it generally reports the estimate of the residual variance as one of the parameter estimates, and it also gives us a t-statistic for that. So, it gives us perhaps a little bit more information than the standard regression model. Okay, anybody got any questions on that? No? Okay. Right. Well, what I'm going to do now is I'm going to take a look at whether or not there is still anything left to explain in the data. Okay? I fitted a model here and done reasonably well, but maybe I can do better. So what I'm going to do is I'm going to look at the correlogram of the residuals. So I'm going to go to View here, then Residual Diagnostics, and look at the correlogram of the residuals here. Okay. What I'm doing here is to see, is there still anything left in the data? Is there still anything left that can be captured or explained from the data? Ideally, what I want is a correlogram that's perfectly flat, with all the autocorrelations lying within the standard error bands. I'm probably never going to get a perfect correlogram like that, but I want to see whether or not there is anything obvious here that can still be explained. So if I look at the correlogram here, okay, you see that a lot of the autocorrelations are actually very, very small now. Okay, just putting in that moving average term has meant that the correlogram has basically become a lot flatter. The one that I would say really stands out here is the autocorrelation at lag 12. Now, again, knowing your data is quite important here because this is monthly data. So the fact we're picking up a significant lag or significant autocorrelation at lag 12 is reasonable with a monthly data set, because what it's capturing is some sort of seasonality, some sort of seasonal element in the data that recurs every 12 months. So we very often look for significant autocorrelations at seasonal lags, the lag corresponding to the frequency of the data. So we've got here a significant autocorrelation at lag 12, and I would say, well, yes, that probably captures some degree of seasonality. And what I should be doing, because I've got a single spike here, is putting in a 12th order moving average component. Okay, so that's what I'm going to do. So I'm going to go back to my model, and I can do that here with the estimate here, and I can add here MA12. Okay, hit return. It's now estimated the model with moving average 12 term in it as well as 1. You can see my MA12 term is coming in with a t statistic of 4.03. The R squared has gone up a little to 0.385, not massive amount of extra explanation, but I'd say it's still reasonably valuable. Okay, so I would think this is probably going to be my best stab at the model, but I'll just go one further round of looking at the correlogram. Okay, and if we look at the correlogram here, again go to the residual diagnostics and look at the correlogram of the residuals. Okay, the correlogram is now pretty flat. Okay, there is always a danger here of what we call overfitting a model. You can go on adding and adding moving average or autoregressive terms to try to capture every single feature of the data set. Really, that's to be avoided, because what we do is we end up fitting a model to a particular data set, but then that model doesn't necessarily perform particularly well outside the period of the data set. So even though one or two of these autocorrelations do lie outside the standard error bands, and if you look at the significance here, it's testing for the significance of the autocorrelations using the Q statistic here, I would argue this is probably a good place to stop. This is probably about the best model that I'm going to get. Okay? So if I just click on stats here, that's going to be my final model. Okay. Now, I've fitted a model to the data. Okay. It's probably not very informative to look at the fit here, but if I just click on actual and resids, that's the actual series is the red, and the green line here is the fitted values. In this case, where we've got so many data points, these graphs are often not very informative, but I'm just making you aware that you can look at these things if you want to. What I'm going to do to finish on this is I'm going to actually use to apply this model. Okay, what I've done so far is I've fitted a model to data. Why do we do that? We generally do that because we want to use this model in some way. And very often the thing we want to do with it is we want to use it to forecast the future values. Okay? So what I want to do to finish on this model is to just show you very briefly how you could go about constructing a forecast. Okay? So we've got data here, we've estimated the model up to the end of to the first month of 2004, January 2004, but we've got another year's worth of data up to 2005. Okay? So what I'm going to do is take my model here and I'm going to forecast with it for the year that we've got data. So if I click on forecast here, it asks me what do I want to forecast. Now we can choose to forecast the original series, oil C, or its first difference to the logarithm. I'm really interested in the original series here. I'm not interested in the first differences of the log. That was just a convenient transformation in order to estimate the model. Okay, so what I'm going to do is I'm going to opt for this, but then I'm going to change my forecast sample down here, okay, to 2004 quarter 2 through to 2005, month 1, not quarter. Okay, what it will do if I click on OK is it will calculate the forecast, which it plots here in blue, and standard error bands here, okay, and then it calculates the whole set of statistics associated with the forecast here, forecast evaluation statistics, which I'm not going to go into here, but if one is interested in forecasting, generate some interesting information for us. Okay. What I am going to do to finish this off is just take a look at how successful this model has been in forecasting. If you notice, what it's done is when I used the forecast option, it created a new series here, oil CF, with the F here being the forecast values. So it's now stored the forecast in this series here, and what I want to look at is the actual and the forecast series to see how successful my forecast has been. Okay, so I'm evaluating it against actual data. So what I'm going to do is I'm going to set the sample here to be, I'm going to choose the year before, 2003 1 up to 2005 1. Okay, and then I'm going to plot the two series, so that's oil CF and oil C, the actual and the forecast series. And if I hit return there, okay, then this is what the model is forecasting. Okay, up to 2004 quarter 1, that's just the actual series. So the red series here is the actual series, and then the actual series after 2004 month 1 is given here, and this blue line here is my forecast. Okay, it doesn't look particularly impressive. It's not captured a lot of the variation in the series, but it's better than just a straight line. It's certainly capturing some of the ups and downs of the series. So we are doing something here in order to forecast this that's better than just a naive forecast that the series will stay constant. Okay, so that's how you can generate a model on the basis of data, and how very quickly you can use that model to forecast. Okay. So I'm going to switch over now to the laptop and take a look at this series. And what I want to do is fit an ARIMA model for consumption here. Okay, so first thing I'm going to do is just take a look at my series. That's my series. Okay, I want to fit a model to that data, so what I'm going to do is use the command line here to type show log CONS. Okay, again we can look at this in different ways. We can plot the graph of the series, which has got the features I've just noted, and what I'm going to do now is I'm going to look at a parallelogram of the series. Remember, the parallelogram's my basic tool that I use when I'm diagnosing what sort of ARIMA model to fit to this series. Okay, right. Okay, now this model is a bit different. The first thing we note is that, again, we're picking up a very slow decline in the autocorrelations. This is characteristic of any series which is not stationary, which has got, for example, a trend in it. So what I might try doing is the same thing that I did for the previous series. Difference it and see whether or not the difference series the parallelogram looks any better. Okay, so let's take a look at that and see what happens. If I go to view here, look at parallelogram, then it offers me the option of looking at the parallelogram of the first difference of the series. So if I click that, okay, that's my parallelogram of the first difference of log consumption expenditures. Now, it's nowhere near as neat as the parallelogram that we looked at for the previous series. It's certainly, the autocorrelations behave very differently. They very quickly die down to zero, but then any fourth lag here is coming through enormously significant. So what I've done by taking a simple first difference of the series is I've found that every fourth lag, 4, 8, 12, 16, the autocorrelation is very, very high indeed. What's going on here? Well, what might be going on here is that these fourth lagged autocorrelations here are picking up the strong seasonal pattern in the series. What we've got here is every fourth quarter, the first difference of the series is highly correlated with its lag 4 quarters ago. Okay? You'll see it even more strongly actually if we just look at a straight plot of the series. So if I look at a graph of the series here, okay, sorry. Let me show here D-log cons and just look at a straightforward graph of this series. So I'll go to graph. Okay. That's what's happened by taking the first difference of the series. Because I've got a strong seasonal pattern, what's happening is every fourth quarter I get a huge increase in consumption expenditures, and then I get a big crash in the first quarter. And it's picked up that regular seasonal pattern. In fact, what it's done is it's even enhanced that seasonal pattern. By taking the first difference of the series, I've got an even stronger seasonal pattern here. Okay. So first differencing might not be my best strategy here. Rather than take first difference of the series, it might be better to take a seasonal difference or a quarterly difference to try and allow for this feature. Okay? So what I'm going to do is I'm going to scrap that for the moment, and I'm going to take a look at the seasonal difference of the series. And to do that, I can do the following. I can type dlog cons 04. Now this is the eviews command, which says take the log of consumption and then take the fourth difference of the series. So compare log consumption at date t with log consumption at date t minus 4. Okay? There are two numbers here. The first one is when we issue this command. The first number is the number of ordinary differences, first differences to take. The second number is the order of what we call seasonal differencing. In this case, fourth differencing of the series. Okay? So let's take a look at that. If we look at the graph of the series, what you'll see is something quite interesting. Okay? I've taken seasonal differences of the series, so what I'm doing is I'm always comparing the quarter in each year with the same quarter in the previous year. So this is one way of allowing for a regular seasonal pattern in the series. And by taking the seasonal difference here, the fourth difference, you notice my series doesn't appear to have any strong seasonal pattern. Okay? It's effectively dealt with the seasonality issue by taking those fourth differences. So that's the series I'm going to work with. rather than taking the first difference of the series, because I've got this very strong seasonal pattern, I'm going to take a seasonal difference, or a fourth difference of the series. Okay, any questions? Right. After that, the process is very much the same as it was before. First of all, I'm going to go to View. I'm going to look at the correlogram here to see if there's still anything to explain in the data. So this is the correlogram of the fourth difference. Now, if we look at this, what do we see? Well, we see autocorrelations that start off positive and then die down fairly quickly to zero. That's characteristic of a first order autoregressive process. That's confirmed by the fact if we look at the partial autocorrelations, we get a significant first order partial autocorrelation, but then after that it goes to, or disappears, it goes very quickly to zero. Okay? So my first model that I'm going to fit is I'm just going to fit in a first order autoregressive process to this to see if that will capture the data. So I'm going to shut this down. I'm going to go to the command line. I'm going to type in ls dlog consumption 04, and I'm going to fit in a first order autoregressive process to that series. If I estimate that, okay, this is the model I get. You see the autoregressive term is 0.71, its t statistic is 15.9, so it's quite significant. The R squared for this is 0.51, so it's explaining a decent fraction of the variance of the series, given that it's there's no trend in here. So you know, it's certainly a step in the right direction. But again, exactly like I did with the previous case, I want to see whether or not I can do any better than that. So what I'm going to do is look at the correlogram of the residuals for this model. So I go to View here, okay, and then look at Residual Diagnostics Correlogram. Click on OK. Now again, I'm looking for a correlogram that's flat, okay. The first few autocorrelations are quite small here. They're within the standard error bands, but you notice that the fourth order autocorrelation is still quite significant. Again, not surprising. This is quarterly data, so we've got 4 observations per year. We very often get significant autocorrelations at what we call the seasonal lag. So what I'm going to do is put in a moving average term of order 4 to capture that fourth order autocorrelation here. Okay, so I'm going to go back to estimate here, and I'm going to put in here an MA4 term. Okay, you see the fourth order MA term comes in quite significant with a t statistic of minus 9.23. The R squared has gone up a bit from 0.5 to 0.62, so it's actually doing quite a lot for me, so it's quite useful to have this term in. Okay, so basically that is where I would end up finishing with this model. This model seems to me to capture the main features of the data, but I can again just go back to the correlogram and take one last look at it. So this is the correlogram of the residuals, and you see now that it's very, very flat indeed. All the autocorrelations lie within the standard error bands. There's not really anything left in the data to explain here. Okay, so that's my final model. So let me just go back to the model itself and take a look at it. Okay, it might be worth looking at the graph of the residuals here. We might get a little bit more explanation, feel for it here. You see here the red line is the actual series, the green line is the fitted values, so you can see that it's actually capturing the data reasonably well. Okay.